And then I can just link to this piece. So if you can stay, that's fine. If not, you can just watch it later. But I really want to get this out today. So if you have to go by, if not, yeah. Okay. All right, so let's talk about springs really quickly. I anticipate no more than like 15 minutes. I'm really sorry. If you have to go, that's fine. Springs. So springs are conservative force. And that force is given by something called Hooke's law, which says F equals negative K delta X. No worries, Michael. I realize that people have to go. You probably have classes. So I'm just going to talk and not wait for responses and things. And so hopefully this will only be like 10 minutes. Thank you all. I appreciate it. So Hooke's law, hopefully you have seen before. This is a magnitude. K is something called the spring constant, which is a measure of how springy the spring is. Right? And delta X is the displacement from equilibrium. So if you have, say, a spring and it's just hanging here, right? Or if it's just, we'll do horizontal first. You have a spring and it's just chilling out. This is its equilibrium position, X naught, equilibrium. If you then take that spring and pull on it and stretch it out, this distance is how far you have pulled it. The force that it took or that it takes to hold it at this extension is going to be your, if this is an absolute value, this should not be a negative, K delta X. So if K is like 100 newtons per centimeter versus K is like 10 newtons per centimeter, this is like a stiffer spring. It's much harder to extend it. This would be sort of a looser, weaker spring. You can just kind of go, right? Not a lot of force to pull it the same distance. Okay. How do you measure the spring constant? It's really easy to do vertically, right? You have a spring, you attach a weight to that spring. How much weight did you attach? I don't know, let's say it's 20 newtons. How much did it pull down? That's my delta X. So my K is going to be 20 newtons divided by delta X. Okay. So this is not super complicated. You might also see it written as Fx equals negative Kx or negative K delta X. The negative means that it's a restoring force. So if you pull it, right, let's say you have K is 10 newtons per centimeter. You pull it out to 3 centimeters from the equilibrium position. So it was like this. You have now pulled it 3 centimeters out. How much force, out, said that like Canadian, how much force are you applying to hold it there? You apply 10 newtons per centimeter times 3 centimeters is 30 newtons. So you are pulling with 30 newtons. The spring is pulling back with 30 newtons, right? If we have our weight here, gravity is pulling down with 20 newtons. The spring is pulling up with 20 newtons. It's always balanced kind of in that way. And you might notice that it is in the negative x direction, right? So if x is positive to the right, your force of the spring in the x direction is going to be negative to the left. And the same thing happens if you squish it. If you squish it by 3 centimeters, then you have to push with 30 newtons to hold it there, and the spring is pushing out with 30 newtons. So your x is negative to the left. Your F spring is positive to the right. Okay. All right. Hopefully all this is making sense. So if you've already compressed it, 33 centimeters. If you want to compress it more, you need to apply more force. So this is a case where our force depends on distance. Right? So if this is x, right? When x is positive, I have a negative F. When x is negative, I have a positive F. This is F spring in the x direction, right? So that means if I want to think about the work done by compressing this spring, I have to do the integral. So from, say, 0 to, let's say 0 to 3 centimeters. 0 to 3 centimeters. So say here is 3 centimeters. I know we're going to do the same K. This is 30 newtons. Okay. So the spring does negative, well, really it's sort of 1/2 base times height. So the spring does negative 45 joules of work as it is compressed. So as you compress it, it is doing negative work, which makes sense because that means it is storing 45 joules of potential energy. And then you did 45 joules of external work to compress it. So our total work is 0. We had 45 done by U minus 45 done by the spring, which makes sense because the spring was at rest. We moved it, we squished it, it's still at rest, right? This is like the elevator way back here. Right? The net work done was 0 because it started at rest and ended at rest. Wow, I did a lot today. Okay. So does this make sense? Our work done by spring is negative 45. The work done by U is positive 45. The change in the potential energy stored in the spring is positive 45 joules. If we release it, the spring is going to do positive 45 joules. It's going to lose that 45 joules of potential energy, and that's going to go into 45 joules of kinetic energy. Hopefully this is all making sense. This expression here, we did 1/2 times the distance times the force. But we know that the force is already, these are absolute values, absolute value of the work done. I don't want to worry about signs right now. Okay, delta x. So 1/2 k delta x squared is the work done by a spring. Also, you can think of it as the energy being stored in a spring that has been compressed or extended a distance delta x from the equilibrium position. Which makes sense because if we do the integral of fx dx, the integral negative kx dx, this is the work done by the spring, the value, negative 1/2 k x squared, right? And our change in potential energy is the negative work done, so that is 1/2 k squared. And this is actually a definite integral. So this is actually delta x squared. It's actually delta x squared. Usually x initial is 0 or x final is 0. Almost always. Okay. This is if delta x is from the equilibrium position. Otherwise, what you have to do is if these are both displacements from the equilibrium position. So this is sort of the example of like the spring has only released halfway, like you compressed it by 3 centimeters and then released. What's the energy loss after it is halfway? at least. So that would be like when your delta x initial would be 3 centimeters, your delta x final would be 1.5 centimeters, right? So you would not do 1/2 k 1.5 squared. You would do 1/2 k 3 squared minus 1/2 k 1.5 squared. Hopefully that makes sense. This is important. I don't think I've talked about this in the previous semesters. Yeah. Okay. I think that's all I want to talk about for springs. What I'm probably going to do is post a little thing about some little practice things for springs on Canvas. And then you can sort of see how it goes. All right. Thank you to anybody who's still here. I'm going to stop there. Thank you so much for your time. And have a great weekend. Yeah. Hello. Bye. Stay